One. Yo, what's up, people? This is Robert Bassano. I got John. I got my boy Mark Diesel. All of us, man, we are on this quest to figure out, man, what all this science is about. The discovery of everything, which is basically nothing. Man, we are on this quest to figure out, man, which is basically nothing, and the location of all stars in the firmament. Now, I'm not going to say for a fact, all right, definitively, but I put up a video before this broadcast coming to my own conclusion. But together, all three of us, and with you guys in chat, we're going to try to figure some things out here, all right? Because I believe I might have located where the firmament may be and where all the constellations are. And that'll answer some other questions regarding where the moon is, where the sun is, how the atmospheres work, and what stars really may be, so on and so on and so forth. And you people out there who are, really into the Bible and religion, um, there may be some proofs for you. Okay? So I'm going to let John take it away. He's going to go about 10, 15 minutes explaining some things. I'm going to let him explain what it is he's going to explain. And then Mark Diesel and I and everyone else, we're going to try to ask John some questions and verify a few things, confirm a few things, argue about a few things, and debate a few things. Okay? So, John, you got it. I'm going to mute the mic. Go for it, buddy.
I'm going to go ahead and share the screen.
Oh, yeah, I got to share my screen. You mean share your screen?
I'm sharing my screen.
Okay. Hang on a second here. Let me present to everybody. All right, brother, man. You got it. Make sure you blow it up so everybody can see it, man. People don't like that. Put on their damn glasses.
Yeah, I got it blown up. I'm watching a watch page. It's not up.
Hey, what's my name?
Mark?
What does it say there? What does it say on there?
Diesel.
Oh, does it still say that? Oh, okay. All right.
Are you sharing the screen, Robert? Yeah, now it's popping up. All right, we ready?
I'm ready.
All right. I wanted to consolidate this and make it a little bit more concise, and maybe it'll become a little bit more clear. So this is the traditional double slit experiment, and we're going to be using photons here, but you could use anything, photons, elementary particles, atoms, molecules, it doesn't matter. So these are the results that you get. You either get no interference, you get two columns, or you get an interference pattern. The overall pattern is either two columns, like I said, no interference up here, or interference or wave-like here. In both instances, particles are hitting the detector or photographic plate. You can see them here, and if you focused or zoomed in on these, you would see the same thing there. There's particles hitting here. So the problem, if they are Newtonian particles, we should only see no interference, this right here, to the left. But we see interference over here on the right. So, what are they when we're not looking and when they're traveling? Why is it when we look or we measure where they are before they reach their destination or photographic plate, the pattern changes? We get a standard particle pattern, this one over here. So, pull this down. So this is the typical Young's double slit experiment. It has no photon detectors. Light source gets thrown at the double slit, and you get on the photographic plate the interference pattern. So then they got clever and said, well, what's going on at these slits? So they put photon detectors over here. And when they did that, the pattern changed on here. So you had two camps. This is what it boils down to. The photon detectors are causing wave function collapse, or knowledge of the which path information is causing wave function collapse. So the quantum eraser experiments were designed to settle this question on the mechanism of wave function collapse. So what do? Well, we go to the scientific method, right? So step one, observe a phenomenon. Photons, elementary particles, atoms, or molecules exhibit both wave-like, that's interference patterns, and particle behavior, no interference patterns. Step two, the hypothesis. If the which path information is known or can be known, then we will observe no interference, or wave function collapse. Conversely, if the which path information is not known or erased and never can be known, then we will observe interference, or the wave function intact. And as we talked about before, we have a null hypothesis with this. If the environment is the mechanism for wave function collapse, that is, decoherence, that's interaction of quanta with a physical measuring device, in this case slit detectors, then we will not observe any change in pattern between detectors D1, D2, D3, and D4. That is, all the detectors will denote no interference. So, the independent variable here is in the experimental setup. There are known paths, D3 and D4, and you have unknown paths, D1 and D2. So the independent variable is the thing testing the hypothesis. The dependent variable I took right from the paper. It was predicted that the joint detection rate, R1, that's the joint detection rate between D0 and D1, and R2 will show interference pattern when detector D0 is scanned along its x-axis. This reflects the wave property, or both path, of the photon 1. However, no interference will be observed in the joint detection counting rate, R3 and R4, when detector D0 is scanned along its x-axis. All right, so we set the experiment up. And this is the delayed choice quantum eraser. So we're going to play this video here in a couple minutes, but let me finish this up. So the results. So as you can see, for the unknown paths, you get interference patterns, R1 and R2, over here and over here. But for the known paths, you don't get any interference, right? That's pretty clear. It's pretty easy to see. So, step 4, you analyze the results. As you can see with the results above, the which path information coming from either slit A or B, which was erased, obfuscated, or lost by the experimental setup for R1 and R2, so the photon acted in a way as if it went through both slits. It displayed an interference pattern, the same pattern as the traditional double slit experiment without slit detectors. But for R3 and R4, the which path information was known due to the experimental setup. It displayed no interference, the same pattern as the traditional double slit experiment with slit detectors. Since there weren't any slit detectors whatsoever in this experiment, that is, slit A and B path information was either known or unknown merely by the experimental setup for each of the detectors downstream. So then, step 5, you validate or invalidate your prediction. Well, we already did that. The alternative hypothesis is validated. There is no possibility that slit detectors collapse the wave function. Therefore, the prediction is confirmed. Knowledge of the which path information solely collapses the wave function. Conversely, the null hypothesis is falsified, which we just seen in figures 1 and 2. That is, decoherence is incoherence. And this is the kicker. The gobsmacking implication here is that not only are there no slit detectors at the double slit, but the which path information isn't revealed from the photon's perspective until the end of the experiment, until it reaches a detector. That is, the photon knew that you knew where it came from and where it was going to end up before it ended up. and changed its behavior accordingly. So, alas, we live in a virtual construct. Question, who's the programmer? So let's read together.
Neo.
You all ready? In the beginning, God created, right? Let's do it again, and again, and again. There you go. Go ahead, Robert. Go with the video.
Hey, can I ask a question first?
Yeah, go ahead.
Okay, you go back to that spot where it says there's no possibility that the detectors altered the, yeah, right there, right there. There's no possibility that slit detectors collapse the wave function. Now, how, again, how do we know that there's no possibility?
Because there is no slit detectors. There are none. If we go up here,
Whoa. There's no slit detectors.
no.
What the hell did you just show?
The slit detect. There's no slit. Here's the slit. Here's the double slit.
Okay, gotcha.
There's no detectors, no slit detectors here.
In the delayed choice eraser, there's no slit detector.
Exactly.
Oh, okay.
In the original one, there's slit detectors, though.
Yes, because that's the double slit experiment. We're moving on. We're going to the question. Okay. We're going to these two positions.
Okay, can I ask a question about the original double slit?
Sure, there you go. Let me pull it up right.
Yeah, that's good right there. Okay, now with this one, correct me if I'm wrong, when they did the original one, they turned the recorder off. The detectors were still detecting, but they weren't recording any data, and you got the interference pattern, correct?
That's correct.
Okay. Now, because I don't know, I'm asking this because I don't know. I tried to look for it a little bit last night. I couldn't find anything. Maybe you know. Did they try just turning off one detector? Like just removing a detector altogether?
Yes, over here. Okay, let's say that we only have one detector, and it's this detector right here on the left.
Okay.
Now, if they fire a single photon through here, if this slit detector doesn't register a photon that passed through here, then guess what?
It either went through the other one or it bounced off and didn't go.
Yeah, it went through the other one, so you know the path information. Yeah.
Okay. So now, was it what kind of pattern did it leave?
Oh, it'll leave this pattern right here if you have detectors at the slits. It'll leave this what they call a clump pattern or two clumps.
Okay. Now, what if there was only one detector, but it wasn't recording?
If it wasn't, now, if the path information is not recorded or stored anywhere,
right,
you're going to get this.
Even if there's only one detector?
Yeah, it doesn't matter if you have one detector or two detectors, and they're detecting, but they're not sending any data, any path information like to a computer or a tape.
Right,
they're just detecting.
Right. But the information's not being recorded, therefore there's no knowledge.
Exactly, and that's exactly what's happening with this delayed choice experiment. But
okay,
yes.
To me, that was my biggest question about how far they went with the different variables on how many detectors did they widen the space between the slits?
Yeah.
Or whatever.
No, but look,
I just don't know, so I'm just asking. You know, you've obviously looked into this a lot more than I have.
Yeah, they were pretty clever about it. They tried all kinds of, and what it boiled down to was the detectors versus no detectors, and whether these detectors were recording something or not.
Right. Okay.
Well, see, this, John, you know, you and I can argue about this to the day we die. And
no, we're not. As soon as you understand it, we'll be good.
No. You make the presumption that I don't understand it, and I'm gonna play the video, and then I'm gonna go into why I'm always gonna have a problem with this, and I'll explain why.
Okay,
Anybody who wants to agree with me will agree on why they should have a problem with it. But let me play the video.
Okay, let me stop sharing my screen first so we have it squared away.
So far, my only problem with it, I think I understand it, and it makes sense. My biggest problem with it, and it's my problem with a lot of things, if I don't witness it for myself, I'm always going to question it.
Yeah, there's nothing wrong with that. Nothing wrong with it. Yeah.
Stop sharing your screen.
Yeah, I did. I stopped sharing. Go ahead and take over, and you can play the
All right,
video.
go to the delayed choice. Play that video for everyone so they can see it. Let me know when they can see it.
Yeah,
Can they
that
see
looks
it?
good, Robert.
Can they see it on the watch page?
Yes.
All right, here we go.
I'm not seeing shit.
You don't see nothing?
I see some stars in your little screen.
Okay, that's what you're supposed to see.
Oh, wait a second, Robert. I'm not seeing it on the watch page. Go ahead and take it over again and pull it up.
Am I supposed to click on
God,
that?
Lord have mercy.
Oh, there we go. No.
Okay.
Did you take over, Robert?
Yeah, I'm taking over now.
Okay.
All right. Present.
It's on your icon at the bottom. It's not on the full screen.
Yeah, I got it.
You know, when a female baboon wants to mate, it presents herself to its mate. Did you know that?
Oh,
It's playing in Robert.
What?
It's playing on your icon. It's not playing on the screen.
Oh, man.
No, I don't see it either.
That's the same thing that happened last time. Okay.
What about now?
I'm not seeing it on the screen.
It
I'm
should
on
come
the
up.
I'm on the watch page. I'm seeing the.
Yeah, it's coming up.
Okay. Okay.
Yeah.
All right, here we go.
There we go.
Here we go.
It might be delayed on here. I'm on the watch page. I still can't see it.
Okay, shut the hell up, please.
The implications because they don't understand the experiments. So I'd like to explain the most famous one from 1999.
Robert,
What?
it's not playing. Okay, now it's coming up. Hold on a second.
I'm seeing it. First, we need to understand what a delayed choice experiment means to do.
Okay, start it over. It's on the watch page. You're good.
Oh, dude, you need to be patient. Shut the hell up so it can play. Mute.
Thank you.
There you go.
Oh, yeah, there it goes. Oh, yeah, I'm not seeing it now.
It's on.
Yeah, I'm just kidding.
Delayed choice quantum arrays can be mind-boggling in many ways. Yet many people misunderstand the implications because they don't understand the experiments. So I'd like to explain the most famous one from 1999 and share the shocking implications of the experiment. But first, we need to understand what a delayed choice quantum eraser experiment means to do by modifying the original double slit experiment. So if you don't know what the double slit experiment is, I recommend stopping here and watching this video on it. Now if you already understand the original double slit experiment, then you know the implications of placing a measuring device at one slit. Without the measuring device, when we shoot photons through a double slit,
Robert, something's happening on the watch page.
through, or which path they took.
Dude, what is happening?
Not
Come on,
playing,
man. You messing up my mojo here, dude. It's playing, dude.
Killing me, Joe.
I'm telling you, it's not playing right.
I see
It
it.
is playing, dude.
Start it over.
Can everyone in chat just give me a thumbs up? You're seeing this video, right? Please.
It's playing, but it's double playing over top of itself. Go ahead and start it over.
You see, everybody can see it, dude. It's you.
Yeah.
You see, you're so involved in this double slit shit, you don't even know your path.
Robert, I'm sitting here watching the watch
wrong
page.
slit. The detector's not up there for you.
Go ahead and start it. Go ahead and start it over.
Come on, man.
Just start it over.
You got smiley face.
Everybody can see this, dude.
Can you please just start it over, Robert?
Yeah, I just did, man.
All right, thank you. Go ahead.
Good job, Robert.
Results of the delayed choice quantum eraser experiments can be mind-boggling in many ways. Yet many people misunderstand the implications because they don't understand the experiments. So I'd like to explain the most famous one from 1999 and share the shocking implications of the experiment. But first, we need to understand what a delayed choice quantum eraser experiment means to do by modifying the original double slit experiment. So if you don't know what the double slit experiment is, I recommend stopping here and watching this video on it. Now if you already understand the original double slit experiment, then you know the implications of placing a measuring device at one slit. Without the measuring device, when we shoot photons through a double slit, we can't then know which slit they went through or which path they took. So in other words, we cannot know the which path information. Now for reasons we'll discuss later, because we can't know which slit it went through, the photon acts as a wave and goes through both slits, interfering with itself and creating an interference pattern. But when we add the measuring device of the slit, we can know which slit it goes through. However, because of this, a different pattern emerges. Instead, we get what is called a clump pattern, meaning we know the which path information, because we looked to see which slit it went through. The very act of obtaining knowledge of which slit it goes through means it only goes through one slit, and changes the result in how the electron acts. Now, delayed choice quantum eraser experiments are pretty much the same type of experiment, except for one big exception. They look to see if our observation is really what is causing the particle to collapse. Perhaps there is something else doing it, and we can trick the system into showing us it. So instead of placing a detector at the slit, two are placed past this, where the particles land. But just before the particles land here, it is pulled away and the two cameras capture the results after they went through the double slit. If they observe a wave, then the particle went through the double slit as a wave. And just observing or knowing the path information doesn't cause them to collapse the particles. So perhaps one could argue what is causing collapse is something else, like interaction from a physical measuring device. But on the other hand, if they collapse to a state of particles at the moment of detection, then even though they went through the slit unobserved, they should produce a wave pattern. The very act of observing instantly transforms them into particles. But not only that, a back history is loaded up so that particles went through the double slit instead of a wave. Well, in 2007, this thought experiment was put to the test, and the results showed that if the film is pulled away, we observe particles. Observation instantly collapses them to particles in one definite position and loads up a back history, so they went through the double slit as particles. Once we have the knowledge of the particle's position, we know the which path information, and this causes a clump pattern instead of an interference pattern. See, observation is about knowledge, a conscious observer having knowledge of the system, and this is what is argued as what causes the particle to have one definite position. The act of observing is the mechanism for collapse. This is better demonstrated from the famous delayed choice quantum eraser experiment from 1999. As you can see, this looks complex, but I'm going to break this down and attempt to simplify what is going on here so we can understand it. I'd also like to thank Ross Rhodes of bottomlayer.com, who has a great commentary on this experiment and was nice enough to reply to my emails and helping me write this. His article about the experiment was actually reviewed by Dr. Kim, who ran the experiment, so it is a pretty trustworthy article. The experiment begins in the top left corner, with the laser firing two entangled photons either through slit A or slit B. Now it is truly random which slit it will fire through. Because we have no measuring device at either slit, we cannot know which slit the laser fires through until they pass through and are detected on the other side. So at each firing, it will either go through A or B. Now the first prism splits the entangled photons and sends them in different directions. The top one goes to detector 0. Now if the photons only hit D0, we don't know the path information, since when the photon arrives, it could have either come from path A or path B. So because we don't know the path information, it should produce an interference pattern if it only came here. If we could place a measuring device at the slit, we would know the path information. But with just a result from D0, we don't know the path information. So because of the lack of knowledge we would have about the system, the particle would act in a way as if it goes through both, becoming the wave of possibilities it could have been, instead of one of these possibilities, if we knew the definite path information. But the other entangled photon goes the other way, and because it is entangled, it will affect the result of its twin that went to D0. Now the other photon from either A or B goes through the prism and hits either BSA or BSB. At both of these, there is a 50-50 chance it will either pass through or bounce off and go to either D4 or D3. Now if the photon hits either one of these detectors, notice what happens. We obtain which path information, because the only way the photon could hit D3 is if it came out of B, and the only way it could hit D4 is if it came out of A. There is no way a photon that came out of B could hit D4, and vice versa. So if a photon hits D3 or D4, we will know the path information it took, and we will get a clump pattern. Now if the photon randomly passes through BSA or BSB, it will either bounce off here or here, and it has a 50-50 chance of passing through BSC or bouncing off of it. So if the photon passes through BSA or BSB, we lose the path information, because if it hits D1, or D2, it could either have come from A or B. We can't ever trace the path information back to A or B. So when they hit D1 or D2, we should get an interference pattern, demonstrating the photon went through both slits, since we don't have definite path information. Now here is one of the important implications of this experiment about what is causing collapse. Some argue physical interaction from the detector is what is causing the collapse, but if that was the case, D1 and D2 should cause collapse every time. But that is not what happens. If a photon makes it to D1 or D2, they always display an interference pattern. Yet every time a photon hits D3 or D4, a clump pattern is formed. But the only difference is what we, the observers, know about these two stations. Because of the experiment setup, we know that if a photon hits D3, it will always be a clump pattern, showing the photon only went through one slit. If it hits D1, we know it will always be an interference pattern, showing that the photon acted in a way as if it went through both slits. But the only difference between these two is what we, the conscious observer, knows about the system. Our knowledge of the system causes different results in how the photon will act. If it was all random and not caused by our knowledge, we should get some clump patterns at D1 and some interference patterns at D3. But that is not what the experiment shows. We always get a clump pattern at D3 and D4 because whenever a photon hits here, we always know the path information. And we always will get an interference pattern at D1 and D2 because we can never know the actual path information. So the photon acts in a way as if it goes through both, whereas at D3 and D4, the photon only goes through one slit because we know the path information. The particles act in a way that correlates to our knowledge. See, what causes collapse is knowledge, and knowledge requires a knower. Sir Rudolph Peirce said, the moment at which you can throw away one possibility and keep only the other is when you finally become conscious of the fact that the experiment has given one result. You see, the quantum mechanical descriptions is in terms of knowledge, and knowledge requires somebody who knows. Now the other implication is even more mind-boggling, because the photon knew beforehand where it would end up. How do we know this? Because of how its twin acts at D0. The twin photon registers at D0 before its entangled twin ends up at a detector, and whatever registers at D0 always correlates to wherever its twin ends up. So if the twin hits D3 or D4, D0 always registers a clump pattern to correlate, and always an interference pattern if its twin lands at D1 or D2. So either the photon has a highly complex computer built into it, so it can know the future, or we have an idealistic picture of reality, and our knowledge of this system affects the past by loading up a back history to correlate with our knowledge. John Wheeler said, it begins to look as if we ourselves, by a last-minute decision, have an influence on what a photon will do when it has already accomplished most of its doing. We have to say that we ourselves have an undeniable part in shaping what we have always called the past. The past is not really the past until it has been registered. Or put it another way, the past has no meaning or existence unless it exists as a record of the present. An experiment from 2012 took this a step further and brought back in the conscious free will of the observer. To understand this experiment, picture two entangled photons are sent from either station A or station B and separated. The first from each pair is sent to one of two different measuring devices here. Observers Alice and Bob are each stationed here, but do not look at their measuring devices yet. Both of the other entangled photons go to a third measuring device, where Victor is. How Victor chooses to measure the two particles determines what Alice and Bob see their entangled photon as. This happens even if Victor decides after Alice's and Bob's devices have measured them, but before Bob and Alice actually view the results. Therefore, a conscious choice affects behavior of previously measured but unobserved particles. Asher Perez, who developed the original thought experiment, says, if we attempt to attribute an objective meaning to the quantum state of a single system, curious paradoxes appear. Quantum effects mimic not only instantaneous actions at a distance, but also, as seen here, influence of future actions on past events, even after these events have been irrevocably recorded. John Wheeler's original thought experiment shows the implications of this. He explained by asking us to imagine a distant star that emits a photon billions of years ago and sends it towards Earth. However, on the way it must pass a dense galaxy. Gravitational lensing will make the light bend around the galaxy so the photon can take one of two paths around the galaxy. Billions of years later, upon reaching Earth, An astronomer chooses to use a screen type of light projector that encompasses both sides of the surrounding space, without focusing on a specific region. Therefore, the photon will land somewhere along the field of focus, without anyone being able to tell which side it took. So it will display an interference pattern, demonstrating it took both. However, the astronomer could choose to measure the incoming photon with a binocular apparatus and focus on the left side of the galaxy, while the other side focuses on the right side. In this second case, how the astronomer chose to measure means the photon could have only taken one path. It would display a clump pattern. So in this thought experiment, how we choose to measure now affects how the photon acted billions of years ago. Our choice affects how the particle acted in the past. So the factor of time has nothing to do with quantum mechanics. And the interesting thing about this is, John Wheeler based this on the mathematics of quantum mechanics. Mathematically, this is what was predicted, and the exact same result is what we see when we put it to experimental test.
What's that?
Okie dokie. So, and we continue. We stop this.
Yeah,
All right.
I watched
Go ahead, Mark.
that video last night.
What was that?
I watched that video last night.
What'd you think of it?
If if this experiment is true, you know, I mean, I'm just going to accept it as, yeah, it has happened the way that they say it has happened. Okay, without me experience it myself, I will always have a doubt. But that's pretty damn fascinating, and it takes me back to that old saying that knowledge is power. You know?
If what he explained is to be accepted, I have a question. I got several questions for John and for you, Mark, and everyone else out there. If what he explained is that the choice of the observer determines what the photon would do
Right.
before it reached its destination or finished its activity, and it's all based on our collective choice, wouldn't that invalidate the whole experiment to begin with in the first place?
No, it wouldn't. No.
Then why not?
It just validated it. How can it invalidate it?
Well, you're saying that that we can consciously validate the experiment, but when he says that knowledge of the observer, well, we
No,
wait, he did say knowledge of the observer. Did I hear it in Latin? Did I hear it in Spanish?
No. The knowledge of the which path information.
All right, look, you can play semantics all you want.
It's not semantics.
Okay, well, it's playing semantics to me. And here's what I want to ask you.
Well, that's how you.
What's the point? Tell me, what's the objective by say? And I'm gonna again. Here goes devil's advocate. What is your objective with showing that experiment in that video? Is your objective to get us all to collectively agree so that your quantum world stays intact and doesn't start to crumble around you because you have knowledge observers who don't agree what the path is going to be of a particular quantized event?
The question is, from the experiment, are the photon detectors causing wave function collapse? That means, is there something in the environment that's collapsing the wave function?
And that's just an assumption they're making. The fact that
they got it. It's not an assumption. I just showed you the two experiments.
No, it is an assumption. I'm gonna
no, it's not.
And that's why I asked that question earlier. You know,
it's not an assumption.
How far did you take the different variables to remove the detectors as a possibility of affecting the wave?
You just did. You put them past the double slit.
Right.
He said in the video that the presumption was that the detectors was what was causing the photon to behave differently when it was observed and when it wasn't observed. Meaning that you have a clump pattern when there's no detector, But when you have a detector observing,
No, you have a
an
clump.
interference
No,
pattern.
no, wrong. You have a
How is that
clump.
wrong?
You have a clump pattern when there are detectors.
No, I'm talking about the original double slit experiment.
Yeah. Okay. Here you go.
I'm talking about the original double slit
I'm going to
experiment.
screen share. Here we go.
They assumed. Wait, hold on, man. Before you screen share everything and show your naked body, man. I'm trying to ask you something here.
No, that would be me. I'm the one in my underwear.
The original double slit experiment was
And
based
that's
on
what
an
I'm
assumption that the detectors were actually affecting the behavior of the photons when they hit the screen. Okay? Meaning when there was no observation at all and the photons go through the double slit, then you had, these solid lines.
No, you had an interference pattern then. Go ahead. Let me share my screen.
Okay, vice
I'll go
versa. You
back to
had
it.
an interference pattern. My thing is this: they put the detectors on the other side. So why am I supposed to believe that just because you put the detectors on the other side of the
I think
Because they eliminated the variable of the detectors at the
but
slit.
that's just the best guess that they're assuming that the observation is actually is affecting the experiment on the other side.
Let me screen share it again. Let me
Yeah, because
explain.
I think I'm going to have a question that'll help out with this this dilemma here.
Okay, 1 second. Go ahead and let me share the screen because we're going right back here. Here's the original.
Click the green button on the left-hand side that says screen share.
I did.
I'm going to need another beer.
Okay, go ahead.
Okay, I'm screen sharing.
Go ahead.
Liar.
Okay. So
I don't see it.
this right here on the right is the original double slit experiment. It had no detectors or anything. Young shot this light through a double slit, and he got the interference pattern. So what happened years later is some Weisenheimer got the idea and said, after the Einstein proved that photons were particles with the photoelectric effect, and Compton scattering went ahead and confirmed that photons were particles, then why were they getting this pattern? So some wise physicists said, well, what's going on with these slits right here, and put photon detectors here. When they did that, it changed the pattern to a clump pattern instead of an interference pattern. So they said, what on earth is going on here? So the two camps were, like I said, there's only two choices here. The photon detectors are causing the wave function to collapse and giving this pattern. Camp number 2 said, nope, it's not the photon detectors, it's knowledge of the Witch path information. So to resolve the issue, they gave you this. This resolves and answers the question.
Now let me ask you a question here, John.
Go ahead.
When they do this experiment, and let's say they turned the recorder off on D3, but kept the recording going for all the other ones, D2 or D1, D2, D4. What's the one up top? Is that D0?
That's the D0. This is the one that's measuring position.
Okay, now if they recorded everything but D3, now correct me if I'm wrong, but D3 would show an interference pattern, and all the other ones would show the clump.
D3, these detectors, D4, D2, D2, I'm sorry, D3, and I can't see these, D3, D2, D2,
okay,
whatever, all the detectors besides D0, these detectors are merely catcher's mitts.
Right.
Right? So if they turn this off, I don't know what you mean by turn it off. You won't get any detection if you turn it off.
No, not turning it off, but not recording the knowledge.
The knowledge isn't being recorded. You already have the knowledge from the experimental setup. There's no knowledge being recorded.
Yeah, here's the thing. This experiment was created based off of what they were trying to prove. What that the original double slit experiment, the detectors are on the other side.
Okay, let me go ahead and put the alternative.
Just say yes or no. The detectors were on the other side of the original experiment, right?
The original experiment, there were no detectors. This is the original experiment here.
Right, get a waveform.
the Young's double slit experiment is here. Then they got wise and said, why is this happening when these should be particles? And they said, let's take a look at what's happened at these slits. And as soon as they did that, they identified where the position of the photon was. They got this. So they said, what the heck is going on? And they came up with these. These are your only two options. The detectors are causing the wave function to collapse, or knowledge of the which path. Do you see the two choices?
Yeah, see, the problem for me is this. What did these scientists think that they could outsmart a photon to trick it into thinking it can't be observed and be detected? That for me, having the detectors on the other side, D0 through D4, I'm up to the belief that as soon as those photons go through slit A or B, they're immediately aware that there are detectors out there.
They're aware. How can they, are you saying photons are alive?
I'm not saying photons are alive. I'm saying that the knowledge path has already been predetermined as soon as they go through the slit.
By who?
If it can happen through observation with the detector on the other side, when the photons were being observed going through the double slit,
There were no.
And they
there
behave
is no
differently
observation
when
here.
observed and not observed. That means the same thing was happening on the other side.
There is no slit detectors here. You can't observe anything. All you're getting
is that the original experiment. I watched the video fucking a half a dozen times. They said that the particles behave differently. The photons behave differently when you're looking and you're not looking.
Well, it's not only looking; it's which path information.
Whatever. It's all pre-programmed to me. They keep writing this in papers, and the problem I have is this.
They're not writing it in papers. They're doing experiments.
Okay, I didn't see the experiment.
You're looking at one.
I seen it. No, I don't see an experiment. I see a
this
really.
Is what it is.
I see a really confused schematic.
It's not confusing. You just have to look at it.
I got a question.
Go ahead.
Okay, John. And it probably flew past me, but
that's okay.
I asked the question.
Go ahead.
On these detectors, okay, you know how we got the clump pattern and the interference pattern?
Yes.
Okay, with the delayed choice quantum eraser, on which of these, how can I get a clump pattern or an interference pattern on D1?
There has to be a single path. It's got to be like D3 or D4. Only one path going to D1. Only one possible path going to D1.
Okay, so if it's going through B, the blue line going through the PS prism,
okay,
or whatever that is,
it's going down here,
and then it'd have to go through B5 and then down to D3.
B5? What
B5? BSA, beam split alpha, and then down to D3.
Yeah, it's reflected off. It's not transmitted through. It just reflects off and goes down to D3.
Okay, now that would give me an interference pattern?
No, that gives always a clump pattern because you know the path information.
Okay, so how can I get an interference pattern on D3?
You'd have to have two possible paths to D3.
Okay, so the only interference patterns were shown were on D1 or D2.
That's correct. Let me go up. Wait a second. Yeah, right here. Right here.
Okay, D1, D2 had the interference patterns.
Yeah.
And that was because why?
Because the path information was lost. Look at D1 and D2. Here's D1. Here's D2.
So you didn't know which way where it was coming from?
Yeah, you didn't know which slit because it could either come from A or B. See the red path?
Right.
It could bounce here and then bounce up here, or it could come here, bounce off, transmit through, and come here to D1.
And so oh, this is some shit, man.
Look, if you saw what the guy said in the end, he says, no matter what happens, there's always the detector D0 is always registering a clump pattern or wave pattern, interference pattern, and that determines what you're going to see at D2, D3, D4.
It doesn't determine it. Gives you a clue on what you're going to see.
A clue. It tells you exactly, because whatever happened at D0, when whatever occurs at D2, D3, and D4, that's exactly what occurred at D0 before. That's
before.
That basically defines why they call it a delayed choice quantum experiment. It's
the delayed.
It's a predictive. It's basically based on probability statistics.
It's not.
Okay, if this is going to happen at D0, we can predict what's going to happen in 3, 4 of the
places.
Yes,
because time and space have no meaning in quantum mechanics. That's why. Because this happens before.
The fact that the detectors are set at 1 nanosecond, and it takes 8 fucking nanoseconds to register D2, D3, and D4. I mean, it's just, for me, the experiment just, for me, it just cancels out, because
it doesn't cancel out because you're forgetting your hypothesis.
You don't need D2, D3, and D4.
Yes, you do. Yes, you do. You forgot the question. Your hypothesis.
Look
at the question.
Then what is this proving? What is this proving?
It's proving that the physical detectors are not collapsing the wave function, only knowledge of the which path information.
But with relation to reality as we all know it, how does this relate to reality?
It says that you need. Here, I'm going to tell you. Are you ready?
Oh, here you go with the God thing.
No, all I'm saying is that in order for matter, the physical matter to exist, there has to be a knower first.
And who's the knower?
Jesus Christ.
Oh my God.
There you go. And I'll tell you what. If you don't think that or come to that conclusion, here you are. This is you.
Man, I'm not going to turn this into a religious conversation or discussion.
It's not religion.
Hey, like I said, man, it comes back to the old saying, knowledge is power.
It's not religion.
Yeah, Mark said it. Knowledge is power.
Well, it's not religion.
Knowledge is power.
If you
know, it's not religion.
Power.
There are people out there.
This is experiment.
Who will tell you that Jesus was a made-up individual, a figment of people's imagination.
Well, people can say a lot of things, can't they?
Well, I've also heard that the other side of that is all those other stories of all the other Christs were all made up stories to try to discredit the Jesus story.
All right, and here's another thing that I found interesting from some people I spoke to. The Romans and Greeks recorded everything, just about everything that occurred in their history. And a historian said this, that they looked back into Roman and Greek records as far as they could go, and they couldn't find any data even mentioning Jesus or someone claiming to be Jesus to be put on trial.
Really? Who's this historian?
What?
Who's this historian?
I forgot his name.
Okay, well, when we play the next video, you go ahead and bring that back up. I'm ready for you.
Okay, you ready for me? No, this ain't about trying to prove. This is not going to be about trying to prove God or whatever. People going to believe whatever they're going to believe.
I'm just
letting
saying.
You know, my individual.
So just talk over me. That's fine.
No, I'm not trying to talk over you at all. You're.
Go ahead. Go ahead. Go ahead.
We could go like hours on this. I could ask you who you think Jesus actually is, but you can't produce an individual. You can't tell me. You even know what he. I mean, you're going off of what a book says. That's been changed 499 plus times.
Listen, I'm just telling you that there has to be a creator. So you can go ahead and struggle with who Jesus Christ was and all those things.
Hey,
I'm not going to fight with you about it.
All right, we talked about this yesterday. Who made the creator?
No, what you can't. The creator.
Okay, but how did the creator come about?
He always was.
Was
the only logical conclusion.
I got a question.
Well, just keep talking over me, and then you can.
No, I'm asking you a question, and you're going around in circles.
You're the one going in circles.
Okay, what was the creator?
I got a question concerning the experiment because
you can't. Nothing can create the create. You can't create yourself. It's a logical friggin' implosion.
Okay, but you're saying that there was a creator. So
That's right,
how did
creator.
this form come about?
He didn't come about. He always was.
Was what?
Him.
Him?
He was never created. That
You
would
know,
create.
this brings me to a comical comedy skit I heard with Bernie Mac. When a little girl was downstairs getting milk and cookies, and Bernie says, "What the hell are you doing?" And she was like, "Him downstairs. Him. Who's him?" Now, you and I talked about this yesterday with Mark. Is that when we were going to decide where we were going to talk about the two laws of thermodynamics, the first and second law, nothing can be created. Something can't be created from nothing.
Here we go. So that's a natural law.
Okay, natural law.
Yeah.
So, I'm still trying to figure out what you're defining as being natural.
Okay, here you go. You ready? Anyone who has studied physics, the science of the laws of nature, knows how daunting the task is. Here's another source: scientific law versus theory. A law describes what nature does. So,
based on the laws of nature are based on what?
So, physical laws.
Knowledge of how things are supposed to work?
Okay, so physical laws, scientific laws, and natural laws are all synonymous. Okay, so what's your question?
I got a question about the experiment.
Okay.
Has anybody tried to take that experiment to the next level of having D5, D6, D6, D7, D8, and so on?
No, because scientists have figured out that they can outsmart a photon.
Well, because I'm thinking, okay, if you have D4, or I mean D1, where there's always the interference pattern, right? And D2 has the interference pattern. Is that correct? Yeah, D1, you have the interference patterns. Now, if they have being able to split off from that to go to only one path, would they get a?
Yeah, the one path. Yes. I mean, you already have it in this experiment.
Right. Do you know if they've ever tried to take it to the next level past that?
What's the next level past that?
Well, having D5, D6, D7,
well,
D8.
You could do it. It would be redundant, though, wouldn't it?
Well, I don't know.
Yeah, all it would be is redundant. You already got the two questions asked. These are unknown paths. These two.
Mm-hmm.
R1 and R2. It's a combination of D0 and D1 and D2. Right here. Those are unknown paths. These are known paths. We just answered the question. So we can go on and we could create other unknown paths and known paths. It's redundant. It's already solved.
Says you.
You know, the other day when we spoke, you know, I asked you what you thought, what was your opinion on that Dalai Lama statement, thoughts become things. So if me, you, and Mark were sitting down to conduct this experiment, and there was another paper written out there too called Quantum of Consciousness, where 13 physicists got together.
Yeah, I'd like to see that one too.
Yeah. Oh, dude, I'm not gonna go do it right now. Okay, I'll email it to you. I got the paper in my box files, which I gave you access to, and you have yet to look at a single document.
I got 1,500 experiments confirming what I'm just showing you right here.
All these physicists that you are presenting in your presentation, they all got together. Max Planck, Henry Lorentz, Albert Einstein. They all got together
to conduct an experiment back then.
They got together to test if their thoughts were actually affecting the experiments they were conducting.
They couldn't do these experiments back then.
There was a paper written called Quantum of Consciousness.
Okay, let me say this one more time. They couldn't actualize these types of experiments at that time.
Well, you're basing the information you presented on some of the foundational experiments they conducted to even get to this point.
Yeah, all they did was the Young's double slit experiment. Here you go.
Okay, and the Young's double slit experiment
There
is
it is.
based, and then you have delayed choice that was created.
Yeah, that was in
They're trying to trick a
1999.
They're trying to trick a photon into thinking, okay,
Tricking
we're going
anything.
to see what you're going to get ready to do. Oh, I already decided what I'm going to do because you helped me out with it.
You can't trick a photon. It's not alive.
Okay. So the guy didn't say that. Hey, they tried to trick a photon into thinking something, into doing something else, right? I didn't hear that in the video, right? I didn't hear that in the video.
Is a photon alive?
If you're telling me I didn't hear that in the video, I'll play the video again.
Well, go ahead. Pull it back up again. Let's go over it.
I think what you have to do is when looking at this, just assume that it's true.
You don't have to assume it's an experiment.
No, I mean for Robert's sake, to get into the philosophical meaning behind all this.
It does. All of science, everyone has a worldview or a presupposition. The question is, what do you have supporting your worldview and supposition or presupposition? So everyone has that. We all bring that into everything that we do. But what is supporting that? That's the question. What's supporting mine? You're looking at it.
Well, and Robert, what'd you say that quote by the Dalai Lama? Knowledge is what?
The Dalai Lama said, thoughts become things.
And that kind of goes along this line of this experiment, though. Thoughts become things. When you know something, it can become something. Instead of just being random shit, it turns into something.
Abstractly, in a way, he's correct.
And yeah, I don't know. It's this is some crazy stuff here. Just knowing something can become something.
Yeah, it changes. Knowledge changes the behavior for some reason.
Yeah. Well, it's like ignorance is bliss.
Yeah.
If you don't know, well, you just don't know. You're a happy camper. You're not going to be thinking about some bullshit. You're just going to be going along and watching your.
So this is what I want to do. John, stop sharing your screen. I want to play that section of the video where you talk about trying to trick this.
Okay.
We can do a share screen here. I should be sharing.
Yep.
Okay. So here's what he said.
Okay.
Is really what is causing the particle to collapse. Perhaps there is something else doing it, and we can trick the system into showing us it. So instead of the detector,
you see?
Yeah.
So the whole point of the delayed choice quantum experiment was setting up the detectors on the other side to trick it into doing something else.
Yeah, to trick the system. They had to look at all variables. Yeah. Not tricking them. They're not tricking them.
The definition of what it means when someone sets up a system. It's supposed to follow a specific path, a specific rule, a specific design, schematic on how it's supposed to perform.
Okay.
So this is why I don't trust this experiment. I'm not saying I don't believe it. I'm saying that I don't trust it.
That's all right. I got another 50 for you to go over.
It's based on the original double slit, and they're saying, okay, we can't do it this way, so let's see if we can do it the other way and put the detectors on the other side.
Yeah, that's right. It removes the slit detectors. That's what you want to do.
So what makes you think that a photon couldn't have, a pre-programmed idea of its own to say, okay, I know those detectors
because photons aren't alive. They don't have ideas.
Yeah, but God exists without no other creator that created him, right?
Oh, jeez.
Yeah, okay. Okay.
Yeah, that's right, because he's the creator. You can't create yourself, because that would mean you pre-existed before you existed, for crying out loud.
So you don't believe that someone could will themselves into existence?
No.
No.
No. Because that would mean
there had to be an ultimate beginning to everything, to where something just existed without being created.
Yeah, and the reason why the idea of God is manifest in the majority of people who live on this planet, because that's the only unproven logical explanation of how everything could exist.
it's not unproven.
No, it's unproven.
No, it isn't.
You seen God?
I
You
don't
heard
have to
God?
see God to prove him. I can test
Okay.
his quintessential attribute,
You're just
intelligence.
and again, you're basing it on the collective concurrence and agreement that everyone else believes in.
No, I'm not. I'm basing it on intelligence. I can test his quintessential attribute, intelligence.
Then answer me this. How
Sure.
is it that you have some people out there, especially the ones in chat, who can actually think in far much more detail than God could ever think?
Oh, they can't. But okay, why don't you go ahead and prove that?
Prove it.
Yeah.
All people have to do is just look around themselves and think, this is not right. If I were to do this over again, this is how I would do it.
Oh, really? I'll tell you what. Why don't you make me a fly?
Make you
You
a
have
You mean
have your chat members go ahead and make me. I just want to see
like
a
the
fly.
maggot that comes out of shit that turns into a fly?
I want to see a fly. Go ahead and design one for me.
Here's one thing about design and creation: man cannot create anything.
There you go.
We can manipulate matter. We can design things and use what's already available, but
Right.
mankind has never created anything. They've only used the materials and resources available to it.
Yeah, thank you, Mark. That's the first law of
Yeah,
thermodynamics.
the
You're gonna
first
have.
one,
Go
yeah.
ahead, Robert.
Yeah, but God existed all by him, lonesome, and all himself, and just decided, you know
It's
what, I'm bored out of
irrelevant.
my mind. Poof! Let me create the heavens and the earth.
He had to.
Okay.
The heavens and the earth couldn't create itself.
I've had that circular argument too. You keep saying he
It's not
had
a circular argument. Your argument is the one that's
because
circular.
here's the thing: if I wanted to believe that he, that's what you keep
Show
saying.
us the circularity.
No. I'm not saying about the circular. I've had this argument, the religious argument, before.
It's not religion. I already told you that 10 times.
And God created it all through frequency and vibration.
I know something. I had this argument before, and I had an argument with some guys saying that God's a woman. And the reason why I say it's a woman, because you know what? Being married, my wife we could have very little in the house, and she could find something in that damn cabinet to make a real good damn meal. A
I'll tell you
man
what.
will just look into the cabinet and be like, damn, we don't have any food.
Dude, my wife can't cook worth a shit, man.
I mean, come on, man. All right, so listen, the next thing I want to go to,
I do all the cooking over here.
I want to do the share screen with regard to it coincides with the
Circularity.
with the
With the lasers.
with the whole photon refraction reflection of light thing, and I'm gonna go show you guys this bending light experiment.
Yeah, all I know is it's flat as fuck, man.
We were looking at this, so let me do another share screen here. Hang on, because I want to show you guys. We want to try to basically develop a conclusive agreement with everyone on how the sun is actually putting the light down here on Earth, okay? And I want to pull up some other pictures as well.
Like that picture I sent you?
Yeah, why don't you pull that up? I'll do a share screen with you,
Oh, hell.
Mark, so you can show everyone. But we want to do this first. Can everybody see the screen? Hello?
Yeah.
I don't see a
Okay.
screen.
So let's just say that this is the sun, okay? I'm putting this protractor here. This is the Earth. This level water. This is water below. As you guys can see this. The material below is water for the index of refraction is 1.33. All right? Above is air, okay? Now, I don't know exactly what angle the sun is at, but if anyone in chat knows, someone tell me. But let's just say, for argument's sake, we're going to say that the sun is at a 45-degree angle. This is not the scale, so let's just assume they're saying this is 93 million miles. Of course, the sun's not 93 million miles, all right? But when we conduct this experiment with the sun going through atmosphere, gas and whatever you want to call it, microgravity, very little atmosphere where the sun is, coming down to Earth. It's a spherical Earth, right? Okay, let's just assume. But you're hitting a flat plane surface. So when I fire that laser, okay, when I fire that light, you have reflection off of the surface of the Earth, and you have refraction. You get the light bending at somewhere around, I'd say that's about 34 degrees, okay? However, if the sun were any higher, okay, you have a deeper refraction and a steeper reflection, okay? You literally would have, if you're at 30 degrees, if you if you're at 30 degrees of angle, a projection of light, you have nearly a 30-degree reflection, and you have, I think that's 24 degrees refraction. Okay, let's go to a wave. This is what a wave would be doing, straight back up. Okay, now let me change the mediums here. Let's change the medium. Let's say that what is below is above. Okay, but however, we're talking about being inside our multi-layered pressurized atmosphere, okay, gas. Let's just say this is the sun again. You still have the same amount of refraction, okay, and then in air you have almost a perpendicular, literally a linear line going from 30 degrees to 30 degrees, but you have just a little bit of light bending. But if I change it to 45 degrees, look what you got. If this is the sun, this is how the sun is projecting down on a flat earth, right? Okay, let's go a little bit further. Now we got prisms, all right? So I'm going to move this. This is supposed to be the sun, okay? Let me move this bad boy. Let me move this around. This is the sun. Now, here's something interesting I want to show everyone. Let's just say, for argument's sake, down below is air. Actually, let's say down below is water. Let's try water first, okay? But let's do this. For those who want to believe that the Earth is a round ball, here's what we're going to do. Here's your round ball, okay? Let me go reflections. Let me go normal. Let me put out the protractor here, okay? Let me pull out the protractor. And let's put this bad boy in the middle. There's your Earth right there.
Yes.
Stand by here. Okay, so let me make sure that this is perfectly centered. Okay. Now, this is my sun. Okay, this is my sun. Well, that was my son who just came in, but this is our sun.
That's a good one.
That was my. So let's do this. Okay. Again, anybody knows the direct angle of the sun, you just let me know, but it's kind of moot for this experiment right here. Yes. Kind of moot for this experiment. So let's do this. Boom. There goes your light. That's it. This is for a spherical Earth now. This is for a spherical Earth. What do I have? I've got air above, I've got water below. Okay? So let's change this to water just to see what happens. Let's change this to air. All right? The sunlight would be going directly through the Earth. If I want to go with waves, look what's happening. The light is going directly through the Earth. All right? This is on a ball Earth, if you want to believe in a ball. But look what type of reflection you're getting. You're not getting reflection right back at the sun. You're getting reflection back out into space at multiple directions.
Yeah.
And then you're having what they call neutrinos going right through the Earth. I'll agree with that. But guess what? The way the sunlight would be hitting the Earth, the sun wouldn't be getting any fucking heat the Earth wouldn't be getting any heat at all. It would just be generating its own heat, and it would potentially overheat. So this is what's happening on a ball Earth, okay? Even if I change the frequency, all right, this is at 650 nanometers. Even if I change the frequency of that light, okay, and I lower it, you still got the same thing. It doesn't matter which frequency of light we're talking about, ultraviolet all the way to infrared. It doesn't matter. It does not matter. Now that's on a ball Earth. That's on a ball Earth. Now, let's change that, okay? We're going to take away our ball, all right? Let me reset. I'm going to reset. Now we're going to go to a flat plane surface, okay? We're going to go to how the Earth really is. Put this up here. This is my protractor, and here we go. Here's my flat Earth, all right? I put this in here at 90 degrees. Let me tilt it up a little bit. Okay. Stand by. Come on, man.
Come on.
It's pissing me off. That's good enough. All right. So here we go.
Looks pretty good.
Change the angle of this boy. I got air up top. I got glass, but let me make this water. Okay? Remember, what's above, what's below. Oh, shit. Hang on. I screwed up. Hang on. Move this over a little bit. Come on, man. Okay. Okay, let's move our sun over. All right. Put water down there, and boom. All right, let me move this over a little bit here so that we're... All right, so here you've got reflection out and away proximal, and it's coming almost back to the sun, right? And then you have your refraction, you've got light bending down, all right? This is potentially how the sun would be shining down on a flat plane surface. Now, for those who were watching, you saw what happened when we did it with a spherical Earth. There was reflection back, but it was in multiple angles, okay? Even if I change the angle, hang on. Even if I were to change the angle of incident, look what happens.
Hey, Robert.
This is just go ahead.
Hey, change it to ray, and then change the flat Earth to air and water above it.
So I'll change the environment to water.
The water above because I think you have water
I'll change it below the air.
Yeah.
So here we go. Look at this. This is with sunlight rays hitting the flat plane surface, reflecting off of the flat plane surface, and refracting, and the light bending down. And this bit, let's just say if this was the flat plane landmass surface and you have your waters, light is literally going into the ocean. Light would be hitting the surface, and then the rest of it would be going into the ocean. You got this reflecting back, but you also have light reflecting back to the sun. All right? This is with water up top, air down below. We got a multi-layered, pressurized, gaseous environment. Okay? If I switched it to air at the top and water below, you get a deeper refraction down into the depths of the water. You've got multiple angles of reflection. Refraction back up into the atmosphere is exactly what's happening with the atmosphere. That's exactly what's happening. Even if I were to change this to glass, which some people are saying that the upper dome is some sort of glass, okay? It doesn't change at all. I just changed it to glass. It doesn't change at all. From water to glass, it doesn't change. Not much. It changes a little bit, but not much at all. Are you guys? Is it this showing on the watch page?
Yeah. What if you come directly overhead?
Yes.
Is this showing on the watch page?
Yes.
Okay.
Hey,
All
Robert.
right. Yeah.
Hey, what if you come directly overhead?
Okay.
Zero the angle on the protractor.
Okay. So here's what we want to do. If I go directly 90 degrees, you talk. Oh shit! Damn.
Yeah, that's it.
No, hang on. I'm all over the place now. I gotta move the whole. I see what you're saying.
Yeah.
Having the sun directly overhead. Okay.
Like it is right about now.
Holy shit. Look what you get. If the sun is directly overhead, a flat earth, okay, let's switch this to water. We got air. Let's see what happens when we switch it from water up top, air below. It don't make any sense. The sun is not directly over us. Now, I understand where you might be going with this, Mark. You're saying that this would be high noon?
Yeah. Yeah.
Okay, let's switch that out and see how it would behave if it were a globe.
I think what you might need to do is have a sphere split in half to where the bottom half is the Earth, the upper half is our atmosphere, so that when you can change the upper half to air and have the water above, like you have right now. You know what I'm saying? I don't know if that's possible. Can you do two?
No, you can't. No, I know what you're talking about. This is what you're talking about. So here's your sun. Okay. Here's your sun. This is water below, right? Air above.
Right.
That should changes to water. There goes your water right there. There's your air above. All right. We'll do the wave. Okay.
Well, actually, in the top half of that protractor, can you put an inverted sphere?
I don't think I can do that on this one.
And then have two hemispheres, one below, one above. The top one will be the air. The bottom one will be the Earth.
You can't do that.
Around it.
Yeah, I was thinking about that too. I don't think
you can do that with this virtual experience. But this is what the sunlight would be doing. This is what it would be doing. Even if I change the angle, look what happens. We know that's not what's happening.
Yeah, and just by looking up at the sky, it just doesn't make sense that it's 93 million miles away. Like that picture that I sent you from yesterday.
When you change the angle of the sun, this is around 45 degrees. I mean, even if I were to change this to water and then change the bottom to air, which would be, this is the Earth here below. This is above. This is what we're seeing. This is what's happening.
Right.
This has to be what's happening. Now,
see if you
European Southern Observatory shoots lasers up into the sky at 90 to 110 kilometers, man.
Right.
They're heating up the sodium atoms. They're heating up the sodium atoms, okay, to create artificial stars.
Yeah, I thought there was nothing up there.
So what does that tell us where the star constellations are? The star constellations have to be within 90 to 110 kilometers. Maybe let's go to 120 kilometers. Our entire fixed constellation system isn't even beyond 100 kilometers, man. It's within 90 to 110. And what's happening up there is some high charged electromagnetic activity which is heating up the sodium atoms to give us what we see in the sky at nighttime, standing on the ground with our own eyes. Because when we've seen high altitude balloon launches and these rocket launches, and they look out into space, there ain't nothing out there. It's black.
Yeah.
It's completely dark. Completely. It is completely dark. Our constellations are within 55 to literally 65 miles. And if that's true, and this is coming from the European Southern Observatory, this is their data. This is their data. I took it from their website. I posted a video before we did this hangout. I posted a video before we did this hangout, and they're saying they are shooting this 22-watt laser up into the sky, and it's stopping. Somehow they're getting resistance between 90 to 110 kilometers. That's what they're saying. I don't even know where I would begin to put this.
Yeah, and that's as high as any of the private space agencies.
Well, you know what? I think I see what you wanted me to do before. I see exactly what you wanted me to do.
Yeah, if you can take that, just a regular that hemisphere.
Put this on the bottom.
No, spin that around. Turn that upside down.
Okay.
Yeah, and we'll call that air. All right.
No, you can't change. So you're saying that you want this to be the dome?
Yes. And inside the dome is air, but now you have to put water around that.
And then the environment is water. Holy shit. There you go. There you go, brother. Does that look more realistic for you?
I don't know. I'm trying.
This is supposed to be the dome. That means that light is going back to the sun, reflecting off, and then you have it bending down to the earth.
Yeah, but the sun's supposed to be inside the dome. I don't think you can do it.
Let me see. Let me see how close I can get this bad boy. Even if you bring it in closer, yeah, you just totally change everything.
Yeah. Can you make
I can't. Well, you still have the. No. Hold on. If even when you bring the sun inside, you still have the reflection and refraction, the light bending.
Make your shapes bigger.
You can't. I can't. Not with this. I can't make these.
You can do anything you want.
Dude, I'm telling you, man. This is a set experiment. It's set by Colorado University.
Make that hemisphere bigger.
Mark, I know you're playing with me right now.
There's got to be a way. Always.
You can't do it. You can't make it any bigger. That's as big as you can get it.
What she said.
So these are the prisms that I used. We saw what happens on a globe. We saw what happens on a flat Earth. You see it for yourself. You see it for yourself.
Yeah, I saw it yesterday.
That's the globe. That's what's happening. That's what's happening.
Well, first off, can you make that? Can you make that?
And if you want to talk about a flat Earth with, you know, sort of kind of a half sphere bottom, look what's happening.
Can you make your sun bigger?
Dude, I can't change the shapes and size of these things, man.
Okay.
Well, that was interesting. That was really interesting. Let's see.
Yeah, because, I mean, come on. I mean, given the size of the sun they say it is, if those rays of sunlight were coming at us, they would hit the half circle of the half sphere of the Earth that's showing, that's facing the sun, and the rest of those sun rays, they just don't end. They would fly all the way past the terminator lines.
Yep.
Over and around the dark side of the Earth, and nobody would ever be in darkness, ever.
No. Then look, the way the sun is working, it don't work on a globe.
No.
It don't work on a globe. It has to work on a flat Earth.
Not the way they tell us.
The sun does not do what they say is doing on a globe.
No.
Period.
Mm-mm. Hell, like I was talking to you earlier about that Bob Simmons who put together the latest interpretation of the globe Earth.
Uh-huh.
The artist at NASA who compiled all of the composite images and put it together to make the globe. And on that picture itself, they show a hot spot. They say it's a reflection from the sun.
Oh, that's right.
If the sun is as large as they tell us it is, you are not going to have a reflection that size on the Earth. It's impossible. That's like taking a 4-inch wide flashlight and focusing that down to a tiny little 1 millimeter laser without using any mirrors or any kind of focusing beam. It's impossible.
They say here. They said that this laser guide star facility is exciting sodium atoms located in the atmosphere at an altitude of 90 kilometers. 22 watts of power.
That has to hit a physical structure because you
It's
just
hitting
can't
something
terminate a laser at a given point.
Exactly. So the physical structure.
You can't say this laser is going to end. Its beam will end at 90 kilometers.
Yep, and here they go right here. They said lasers can excite sodium atoms in the mesosphere, which is located 90 to 110 kilometers above the surface of the Earth. So the mesosphere, they're claiming, there's at least 20 kilometers of space in the mesosphere where the stars are actually located. So we just located where all the stars are.
They're saying the mesosphere is 20 kilometers thick?
They're saying the mesosphere is 20 kilometers thick, give or take. So that is where that has to be where every single fixed star constellation is located. In a 20-kilometer range in the mesosphere starting at 90 to 110 kilometers. There's your dome right there. Nothing is getting beyond that point. Nothing. If a laser can't get there at 20 watts, you damn sure a rocket or a space shuttle or a fucking satellite is beyond that point. Period. Period. And somehow the rest of what you see that you think is real is being excited by some sort of electrical current or electromagnetic anomaly, phenomenon that's occurring to give you what you see in the sky. Beyond 110 kilometers, there ain't nothing there. There ain't a damn thing there. Which means that if the stars are at this level, where the hell do you think the moon is at? The moon could be in the damn stratosphere. The moon could just be right at the edge of the stratosphere and mesosphere. Because that's why it looks so damn big. It ain't 238,000 miles. There's no damn way. The moon is 238,000 miles. And if the moon is at a lower altitude, you can be damn sure that the sun ain't 93 million miles. It probably ain't even 500,000 miles.
And like I said, if we can get a half a dozen people, 3 in the northern hemisphere, 3 in the southern hemisphere, outfit everybody with a sextant, we can determine the elevation of the moon.
This is crazy, man. This is the European Southern Observatory. They're saying this, not me. They're saying it.
Yeah.
They're saying our star constellations are between 90 and 110 kilometers, within a 20-kilometer pocket.
Yeah, that's not very high.
Illuminating. Which means, where the hell is Venus? Where's Mars? Where's Jupiter? Where's Saturn? Where's all this other stuff they claim is millions of miles away from us? It's not. It's not.
Well, that's why, you get a lot of these people, they say, well, I'm talking people who dispute the globe. They say the sun is, 3,000 miles up or this, that, and everything else. That's just guessing.
You damn right.
Yeah, and people have to stop guessing. We have to start doing things to help try to prove one way or the other. Or
you guys know where I come from this. I take their own information. I'm not just trying to put it all together. I need for them to say it.
Yeah, which is surprising. Somebody would come out and say that, hey, there is something determinate up there, 90 to whatever, 100 and some kilometers up there, where there's something physical that we can manipulate.
Exactly. And see, here's the thing. They put this information out in open source because they're of the belief that the majority of people on this earth are not going to go looking for this information because they're curious about the world they live in.
Well, plus they won't put two and two together either. They'll just say, oh, that's pretty cool. They can make a star up there. Okay, that's kind of cool.
Exactly. You got people who just, they don't think that people are not going to get together and start piecing together the information they're finding and say, whoa, wait a minute here. I mean, you know, I didn't believe the lunar wave at first because someone said that it could have been a jet plane flying by, you know, and it was the jet wash.
Yeah. Hey, you know what? I'm not sure if I buy into that lunar wave stuff either, because I actually have seen some other videos where people were doing videos of other celestial bodies up there, and there was a wave that went across that also.
Yeah.
And I forwarded that information to a couple of people that are big on the lunar wave thing.
Yeah.
And I've never got a response to any of it. And,
well, the thing I want to say is this: I didn't want to believe that there was actually potentially salt water above us.
Well, and it could be a literal wave.
It could be, but here's the thing: people say, and I put this in the video I put up. You know, you got ice, you got large chunks of ice falling out of the sky, right?
Yeah.
So, is it possible that this ice is freezing because in the mesosphere you've got minus 50 degrees Celsius? Minus 50 degrees Celsius.
Yeah, how can it be that when you got the sunlight coming through from
90 No, but get this. If you really do have that much, if you do have this 20-kilometer concentration of what they claim to be a layer of sodium atoms, if they're under those cold temperatures, or let's just say you have the expansion and contraction of the atmosphere, right? The solar cycle. That means that when this ice comes out of the sky, it's hitting that lower layer of the mesosphere, which causing it to freeze over, and that ice just, boom, density and mass just take over, and that shit just comes back down to the earth, hitting somebody in the head. But what I said in the video that I just put up was, the next time there's a hailstorm, pick one of them bad boys up. Taste it.
Yeah, see if it's salty, huh?
If it's salty, you can be damn sure that what the Bible said about what is below is above, that's exactly what is above us. What's in the ocean is exactly what's above us. And if that's the case, the next thing you got to ask yourself, what the hell is the moon moving around in?
That's some salty balls, man.
Because they said the temperature of the moon is plus 256 degrees Celsius, Fahrenheit, and minus 250 degrees Fahrenheit, which means that the moon is rising and dropping, rising and dropping, and rising and dropping. You can't tell me that it's hot on one side and cold on the other.
Yeah, and we had guys walking around up there.
You know, you can't tell me that.
No.
I don't care what kind of suit you got on. All right, you're in constant temperature at 256 degrees. It's gonna get damn fucking hot. Or that damn air conditioning you got on there is gonna overheat itself and get overworked. It's gonna break down. What do you think would have happened if the cooling in those suits would have actually broken down? Would they have literally cooked inside that damn thing?
There's no way you could make a cooling system that compact with 1960s technology to be able to handle that kind of environment.
Exactly. So,
hey, John.
Yes.
You're being pretty quiet here.
Yeah, I'm just listening to you guys. Go ahead.
Now, for me, I take the European Space Southern Observatory's information as unequivocal. They say they can do that. Do I still want to go down there and confirm it myself? Hell yeah, I do. Hell yeah, I do. Because I want to know if those lasers can fire 22 watts at 90 to 110 kilometers, can you ramp up the power on that bad boy? And could you fire a laser further up into the atmosphere? I am dying to hear what they're going to say, because if they tell me no, that means, oh shit.
They're only using 22 watts.
22 watts. 22 watts. 4,000 times greater than a pen laser.
That's not a lot. Well, I mean, it's a lot, but
yeah, it's a lot. But here's the thing: they have 4 of these things on one telescope. They got 4 telescopes. They can fire and create 16 artificial stars. So if they can create 16 artificial stars, concentrating this laser, you don't think that they can create like a whole body of artificial celestial bodies in one night? And people look at him like, oh wow, look at the constellations.
yeah, a new planet.
I'm gonna be honest with you. I've been focusing on this. I've always wanted to know where could the stars be. I said that they potentially could be in our thermosphere. There's somewhere in one of the layers of our atmosphere. I didn't know, but
Hey, Robert, have you seen pictures of these stars that they've made?
I saw the video that a company Ale did, and yeah, they show a video on ESO's website of them actually creating the star.
Do they look? I'll have to check that out. But maybe you can tell us. Do they look anything like images of stars that we've seen from amateur
Yes.
astronomers? You know, they look like that pulsating light.
Yes, they do.
Interesting.
They look exactly like it.
Wow.
They look exactly like what you see normal in the sky, which now begs the question. And again, I put this in the video. We look at the pyramids. There's a guy out there, Lee Bracker, friend of mine. He focused heavily on the pyramids. The word pyra means fire. Middle. Could the pyramids that have been constructed all around the world in strategic locations been some form of
star makers,
laser-guided facility, just like we have today, where they literally were creating shit that was up in the sky? Or they could have created something bigger, like the fucking sun,
like the moon,
or the moon.
Yeah, because there are some legends in certain cultures where there was a day when the moon did not exist.
There you go. I got a government document that says the same damn thing. The Russians had launched 52 probes before the Apollo program. And you know what those probes were sent out for? They were looking for the moon. This was back in the 40s and 50s. They sent out 52 probes, and the U.S. mistake these launches as though the Russians were trying to develop some intercontinental ballistic missile capability to attack the United States. No, they were looking for the damn moon.
They were looking for it, or just trying to get to it?
They were looking for the moon, and they were trying to get there. One document from the Russian space agency says they got within 5,000 miles. Now there was no reference. I don't know if that was 5,000 miles from the launch or 5,000 miles once they got up in the atmosphere. But they said they got within 5,000 miles. Now back in the 50s, 40s and 50s, there's no way anybody could develop anything to get 230 plus thousand miles, which means the moon had to be closer.
Yeah.
The moon had to be closer. Nothing existed back in that day to get 238,000 miles. Somebody wants me to play the YouTube video. Hold on here for a second. Let me see what it is. Let me see what it is first.
How many people are in chat?
There's 135 viewing. I don't know how many are in chat.
Okay.
We want me to play this YouTube video. So ESO, I'm not going to say that we found the definitive answer, but we found the answer. John, you're going to love this one.
Obviously, love it.
It's a video titled Quantum Quackery. What is light, photon, poppycock, and Einstein's brain fart?
Hey, John.
You want me to?
Yep.
What does Tesla say about quantum theory and mechanics and stuff?
You know what? I haven't come across anything about what he said.
To me, that would be interesting because Tesla was on top of a lot of shit.
Oh, definitely. He definitely surely was.
What's that one thing where somebody asked Einstein, how does it feel to be considered the smartest man in the world? And he says, I don't know. Why don't you go ask Tesla?
Let me play this video I don't know how much of it I'm gonna play. Let's see what this guy has to say. It's down John's.
People who watch the videos that I do on photography aren't interested.
I've seen some of this guy's stuff
videos that I do on
before.
field theory.
I watched something last night on him.
Sometimes,
I recognize the
obviously
name.
so, certainly do overlap, because what is photography other than, of course, if you're a master photography expert in composition and light manipulation. Now, it is an absolute, undeniable fact that every part in human history has always thought that they had a correct handle on the nature of the universe. Believe it or not, however, and this is easily provable, the ancient Platonists, the Pythagoreans, and some Neoplatonic Platonists, which is why I translate ancient Greek, and have been doing so for many years, including ancient Prakrit, had a far, far, far better grasp of cosmic mechanics than we do now. I mean, they literally sat around. I mean, they weren't worried about paying bills and property taxes and buying the latest microwave or DSLR camera. And all you need to do is isolate yourself and have a very logical brain. And there is an ancient lost art, and I plan on writing a book about it, as well as I've written many articles about it. And it's called abduction or retroduction, not like you abduct a child. It is a type of thinking methodology whereby which very abstruse principles of nonlinear comprehension of ontological principles can be understood or grasped. Now, getting to the point of light. Now, it is true that there really only are two people that are intelligent in this world. And I don't mean wise, I'm just talking about intelligent. There is a large group of sheep that you're brought up and brainwashed that Einstein was a really, really intelligent person. But it turns out that Einstein was a moron. By the way, in German, Einstein means one stone, which is a slant, meaning you've got only a couple rocks in your head. Einstein, one stone. Although the name Einstein actually means idiot, by the way. How ironic. Einstein was a moron. Okay? Now, who are you going to trust? There are only two factions in this world. The guy that loved peace and that invented 100% of the modern world, and that would be Nikola Tesla. Okay? The guy that actually understood much of how the universe works. Unfortunately, two gigantic trunks of dynamic theory of the fields was lost forever and is admitted to be owned by the government. And I forget what laboratory they admitted holding it at, but they won't release it. So, and then there's another person who didn't invent anything. Now, he did get a Nobel Prize, not for relativity, which is still a theory. And by the way, that theory has far less credence today, even among his lovers, than it did, say, 30, 40 years ago. That is extremely telling. He did get a Nobel Prize for something else. Now, it is true that accurate observations do not translate into accurate explanations. The photoelectric effect. You probably don't know what it was. I mean, I've written about it in my book on magnetism. But he made correct observations with incorrect conclusions. Now, the entire basis of current physical theory, physics, by the way, physical, is based upon the notion that the cosmic mechanics, or Mother Nature, if you will, is an insane hooker on crack with a bag of magical particles. You see, they can never understand, nor can they explain instantaneous action at a distance, IAED, nor have they correctly explained light. Okay? There is no such thing as a wave-particle duality. As I've told you before already, every age of humanity, insofar as its science goes, has always thought it was right, and 20, 30 years later, sometimes 40, 50, sometimes more, it's always proven. They look back and go, those guys were idiots. They had no idea. They were talking out of their asshole. Einstein has set back cosmic mechanics understanding by 100 years. He is actually starting to wane. I've actually noticed over the past 20 years that those who know who the hell Tesla was has gone like this. Those who understand that Tesla's comments about Einstein, about him being a fuzzy-haired crackpot, and the notion of curved space, which is nothing other than the absence of inertia, the notion that that is something that acts on something is an absurdity. It is equally the case that I could say a shadow would make someone cold if they sit in the shadow of the sun, but I cannot reify absence as something that does something. That is an intellectual fallacy. It is unwise, it is untrue, and it is, empirically so, not viable. You cannot reify absence. Someone can say, well, I toss you out into the vacuum of space and you quickly die because there's no air there. Well, no air, absence of something, is not something that actually acts upon something. Absence itself is a posterior attribute of something else, and it is relational. It is posterior. This is the fallacy of a composition whereby which one reifies absence as principle or subject. And this is the primary fallacy behind relativity and Einstein and all the idiots that believe in what Einstein taught. Tesla knew this was BS and crap. He said as much. The most meek person on the earth, never would harm a soul, said as much. He called him a fuzzy-haired crackpot. He said his followers were stronger of mind, and that eventually the truth will shine out. And of course it will. Now, getting into breaking this into photography, well, that sounds like a long stretch, right? Photographia, photons, photos, light. If you think that the lens on your camera is a light funnel that is funneling in particles to hit the back of your sensor or your film emulsion, then you, alas, have been sniffing the glue of quantum mechanics. There is no such thing as a wave particle duality, and there is not one bit of evidence in this entire universe for a photon. Not one. No one has ever witnessed a photon. No one has captured
Please stop this.
There's not one
No, hang on.
evidence on this entire Earth.
We've heard enough.
Present or hints for the existence of a photon.
No, hang on for a second, Jay. I'm going to play a little bit more.
Oh,
Because
goodness.
I'm glad he's using the camera as an example. Because I said something weeks ago regarding the possibility that if you put a camera up to your eye to take a picture of something, you have already you've already captured a mental picture of what it is you want to take a picture of.
You're breaking up real bad.
Can you hear me?
We can hear you, but you're breaking up.
Yeah, let me stop the video. I'll watch this another time. Let me stop this. What I was saying was this.
It's still bad.
Dude.
I'm gonna have to watch that on my own.
Yeah. So, everybody hear me better?
Nah, you sound fuzzy.
Oh boy, are you guys just saying that to get rid of me?
Maybe.
No. Why would we want to do that?
Heathen.
So, what I'm saying is that you want to take a picture of something. You've already. It's messed up. Let me speak in. Okay. Let me I don't know why it's doing this. Let me go out and then come back in.
Okay.
All right. You guys are already in it. Let me go out and come back in. Oh no, it won't let me do it because I'd have to end the broadcast.
Oh.
That sucks. Let me do the best I can.
Go ahead.
Go ahead and mute yourself.
What was that?
Mute.
Yeah, let me see.
And then come on back.
How about now? Is it better?
It just sounds kind of like you got some interference in there. Maybe back up a little bit, or go ahead and give us a test.
What about now?
That's better.
Okay.
There you go.
So what I was saying was this, is that if you have a camera, whatever you want to take a picture of, you're going to catch physical visual snapshot of it, of what you want to take a picture of. So that image is already stored in your brain. Now when you put the camera up to your eye to look at that object again, based on the research that Tesla was conducting and the development of a particular device, whereby he was trying to develop a tool to capture the image that was projected onto your retina by your brain. The image was upside down, and then he would be able to capture that image using a cathode tube ray device to project the image onto a screen. It was his way of reading your mind, reading your thoughts. So when this guy brought up the issue with regard to the camera, and no one's ever observed the photon and no light is coming through and capturing this light at different spectrums and allowing you to superimpose the image onto a film like a photon detector and then creating the image, I can relate to what he's saying, because if you're looking at something right now, you pick up a camera to take a picture of it, how do you know that camera is not taking a snapshot of what is actually being projected on your retina and then superimposing that image from your own retina onto the camera film, and there goes your image.
Well,
There goes your image.
Well, it's real easy to prove a photon.
Okay.
You take a light and you put it way far away from a double slit experiment, right? You send it through a double slit and you wait until something happens. And guess what happens?
I don't want to guess. Tell me.
You have a little dot hit your photographic plate. A little dot, right? I mean, this has been done millions of times. So it has energy and momentum. It's a particle.
But here's the thing, Jay. I've listened to some of this guy's videos before.
Yeah, he's a great source.
Will you give him a chance?
Yeah, I
What
gave
he's
him
saying? Come on, dude. Come on now. It's like anybody
that was a joke.
What you're saying, you're not going to want to hear it.
That's a joke. What he was saying was a joke.
Come on, man.
I mean, come on. He didn't even get to the punchline. He was talking about.
Well,
I don't know. Who is this guy? Let's see his experiment proving what he's saying.
I'm not sure if he actually did an experiment. Let me.
All right. I'll tell you what. Let's look at this. Here you go. Let's try this. You explain this to me. There you go. It's in chat. You explain that.
No, I want to finish playing this guy's video.
Yeah, and then we can go here and well, why would you want to finish that when you could just play this?
Yeah, but see, you're being biased now.
At 3 minutes, and we could destroy what he just said. It shows you right in front of your face. You already seen it.
You're being biased about it, Jay. You're saying that nobody else. I mean, if they're going against your narrative, you're not even going to want to listen to it.
Well, I have proof that he's an idiot, and here it is. Go ahead, pull it up.
You didn't hear what the guy had to say.
He said that photons weren't particles. So let's stop and let's destroy his claim right now.
Well, I want to let him finish, and then we'll see what
Okay,
else.
then you go ahead and let him finish. Maybe one of his tattoos will jump up and show you.
Oh, come on, man. You got two Navy guys here on the panel. You're Army guys, man.
Look how long this thing is.
Oh, there we go. I'm gonna watch that later.
The entire Earth. Present or hence for the existence of a photon. Light is a coaxial circuit, a longitudinal dielectric with transverse electrical magnetic components, just like the coaxial cable that feeds from your satellite dish to your TV, so on and so forth. A coaxial cable, transverse electrical magnetic components, and a longitudinal dielectric. Now let's get back to the idiot Einstein. Das idiot Einstein, Einstein means idiot, by the way. Einstein wants to...
Okay, I'll stop it there. He said
there's no kind of difficulty. We have two contradictory pictures of...
Okay, I'm going to stop that. And then what I'm going to do is I'm going to click on...
Well, he's correct
Hang on
in
here.
Einstein, but Einstein and quantum mechanics are married bachelors to begin with. So what is he saying?
Well, we'll see what you put up. Oh, here we go with this again.
Zeilinger has proven that no matter how extreme its predictions, quantum theory works, even though it shouldn't. And perhaps the ultimate proof of just how unsettling quantum mechanics can be.
Are you showing us?
Double slit experiment.
Yeah.
It will make you question whether reality exists at all. This simple configuration shoots particles of light called photons, one at a time, through two tiny slits in a screen.
With a laser which produces light, this light is...
You know what? You and I watched this experiment. No.
Oh, you don't have any bias. You don't have any bias. It shows you
I don't
photons
have
right
any
in front of your face.
It's happening on a computer, dude. Come on,
It's not
man.
a computer. It's not a computer. He's showing you the experiment right in front of your face.
Okay, we'll see.
We have a camera.
Watch it show up on a computer screen.
Yeah, because it's just a projection off the screen.
Yeah, it's not a projection off the screen.
No, it's
It's
not.
a software
What are those
program.
thoughts?
It's pretty random.
Oh, what are those?
Travel one by one,
Giraffes?
some through this, some through that slit. You would have...
You know what that reminds me of? That old Atari game I had. I could do the same thing.
Oh, Pong.
Yeah. That's what that looked like. That's why I didn't trust this when John first showed it to me.
Don't try to do it.
I'm going to have to look at what Tesla thought about this experiment and
Yeah, wow.
see what...
mysteriously create a band of stripes. This is what you would expect to see if a constant beam of light shined through the two slits. It would spread across the wall like a wave. So how can single bullet-like particles of light create a wave pattern? This could only happen if the particles go through both slits at the same time. In other words, the particle is in two places at once. But strangest of all is what happens when you put detectors next to the slits. When the photons are being watched, the wave pattern disappears. Take away the detectors and the wave pattern comes back. This suggests that we can change the way reality behaves just by looking at it. Does this mean that reality itself is not real?
The modern answer is that the path taken by the photon is not an element of reality. We are not allowed to talk about the photon passing through this or this slit. Neither are we allowed to say that the photons pass through both slits. All this kind of language is not applicable.
So, do we just keep reaping the benefits from quantum mechanics and accept that deep down nature plays by a set of rules that will forever remain a mystery?
The interesting message here is that we have quantum physics now around for nearly 100 years. And we are still working at the foundations. And that tells me that when we found it, it will be an absolute revelation. It will be something different from what we have been thinking.
If the quantum theorists are correct, we will never understand the fundamental level of the universe. Our hopes of finding an ultimate theory will fail. One race into a roadblock it can't break through. But what if they're wrong? What if the truth about what happens deep inside you, me, and everything else in the universe is there? We're willing to look for it.
Uh-huh.
Yeah.
So,
I don't think I want to know what's happening deep inside me.
so my thing is this. I'm actually going to try to create the double slit experiment. I'm going to get myself the sheet metal. I'm going to see if my brother-in-law can take it to a machine factory and literally laser in 2 slits. And then I'm going to get myself a real strong-ass fucking mag flashlight. The other thing I have to do is get my light detector to capture that light on the other slit on the other side.
Aluminum oxide, I think, is what it is.
Yeah, I'm gonna see if I can get that, and then I'm gonna videotape this fucking thing. I want to see that if yeah, Foss was saying get a laser. So I'm gonna get a laser. I'm gonna fire it through this double slit, and I'm gonna videotape it to see if I see a wave or I see a set pattern. I'm gonna do this.
Okay.
I'm gonna videotape it. Because you know what? I want to see it live for myself.
Okay.
Because these software programs I got to use for school and the shit we're seeing on these videos, I can't trust any of it.
Yeah, I don't trust Morgan Freeman either, man.
I just can't trust any of it. So anybody else out there who thinks they want to do it as well, try it out yourself. But I'm gonna put together my resources to actually create this experiment and do it live for everyone to see. Because we need to know. We really do need to know. We really need to know. So it's been fun. John, you know I got nothing but love for you. If we don't argue the way we argue and fight the way we fight, and I don't wish death upon you, I don't love you.
That's okay. Yeah, we're good.
You know that, man.
This isn't. Hey, one good thing, it's not an echo chamber. So.
Yeah, that's true.
What's that? What's that? What's that?
Yeah,
he said it's not an echo chamber. All right, fellas, listen. If anyone out there has questions, I'm looking in the chat right now. Larry's saying don't use the F word, use cockadoo.
Who said that?
Larry. Larry doesn't want us cursing.
Fuck Larry. No, I'm just kidding, Larry.
Larry. Martin's out there too.
Hey, I want to put something out there real quick.
Wake up out there. Nora's out there too.
Hey, Robert.
Yeah.
Let me put something out there real quick. It's about this measuring the distance to the moon thing. All right.
Okay, go ahead.
I know this can be done. If anybody knows anything about triangular positioning, okay, where you need at least 3 points to fix a position to something, and incorporating an azimuth into that to get an elevation.
Hey, Mark.
Yes.
Did you look at that video that I sent you with Dr. Zach?
I did. I sent him an email, and he says he wasn't really sure that he could help me out. It's I don't know. Maybe he's just busy. It's like everybody else that I bring this up to who's supposedly trying to figure out the truth. They completely fucking blow me off.
Now, you seen what he did with the sun. Can't you get that timeanddate.com and see the lunar elevation angles?
I don't want to go by somebody else's data. We have to collect the data for ourselves.
I got you. Okay, that's fine.
Because here's one thing that I've learned. And people out there who observe the moon and all that other stuff, they can let me know if this is true or not. I worked it out with a right triangle. All right. If you were to take the supposed elevation of the moon at 237,000 miles?
Yeah, something like that.
All right. and have a base, your base be about 12,000 miles long, you couldn't do it with anything less than an angle of 88 degrees looking up at the moon.
Oh, I see what you're saying.
But we have azimuths to the moon of 40 degrees, and
Right.
that would be impossible.
Right.
Come on, man. Yeah, my dog wants up. But the only way you can determine this for sure is to get a triangulated position.
Right.
All right. So, you know, what we would have to do is get at least 2 or 3 people in the northern hemisphere, 2 or 3 people in the southern hemisphere, at the same time on the same night. You know, either coordinating through Google Hangouts or Skype. Everybody would have to be equipped with either a sextant or something else.
Wait, you say you wanted an angle of the moon.
Well, you need an azimuth, which would be the angle of elevation to the moon, and you would need a what the hell you call it? A bearing also. So
Yeah,
everybody would have to provide a bearing and an azimuth to the moon. Then what we could do is put that into AutoCAD and input the information like Dr. Zach did. Okay, and then that would give us the position of the moon and its elevation. And if you do it every 3 minutes, all right, there's something else applied that's called the 3-minute rule. So what you can do is if something travels a certain distance in 3 minutes, it tells you how fast it went.
Okay.
Okay, and then by that we can get a speed. We can, you can do that 10 times within 30 minutes, and you can get an average speed. So if we get an average speed of how fast the moon is traveling,
you and I might be able to do this, Mark, if we get down once we get down to Chile, man. Because down here in Latin America, man, it's kind of raining season, so it's cloud cover. You're not gonna get clear skies unless you're down in Chile.
But you can't do it from just one spot.
Well, that's what I'm saying. We would have to have someone in Chile. You and I could get to Chile, and then we have someone up in the United States do it, and then someone over in Europe.
Yeah, I don't know if you could have somebody in Europe actually see the moon at the same time that the people in South America and North America can see.
Yeah, the only clear place we'd be able to see it is in Chile.
But if you can get like somebody on the west coast of South America, somebody on the east coast, somebody in either central or western portion of the United States and on the east coast of the United States, 4 people, I mean, that would be perfect.
Yeah, I could do it. You got one central right here.
Yeah, okay, you're central, I'm eastern. If we get 1 or 2 people
if you go
from south in the southern hemisphere,
right?
Go to timeanddate.com and pick a few dates where we know there's going to be a full moon.
Well, that's why I want to put this out there. So if there's somebody in the no shit southern hemisphere that actually looks to the northern sky to see the moon, we need somebody like that. We need as many people as possible down there.
It's definitely something we can work on.
All right, and you can pick up a used sextant for $40-50.
Yeah. Nora was saying you can get them on eBay for real cheap.
Yeah.
Nora was saying.
So if anybody's out there who's interested in doing this, who's in the southern hemisphere, who sees the moon in the northern sky, contact us through Robert or whatever, and so we can coordinate something. Then once we have the people in place, we can pick a date. Then we could coordinate over a half-hour period, take 10 readings every 3 minutes. Then we'll get a speed of the moon. And, hey, with the speed of the moon, if we know how fast the moon is traveling through the sky over a half-hour period, then we know how far it can travel in a 24-hour period, which can give us a relative circumference or a relative size of the circle that we just may be on.
I can tell you this here right now. I got a document with that data. It's just John and I were talking about it. It could open up a hornet's nest, man, if I put it out there. So, but yeah, it's best that we just do it raw, man. Because it's just best we do it raw. Because the document I got with regard to the laser shot they did to the moon in 2014 has that data on it.
But that's just one reference.
They have the azimuth angle. It was shot from Chile, and it was just from one location. But they they obviously, the data shows that they were tracking it
Right.
across the sky. So they knew how fast it was moving. They know what angle it was moving at. You know, they have all that data. But yeah, you're right. It's best that we do it ourselves instead of trusting, someone else's data. We need to see for ourselves, and that's what we'll put together.
The first rule of troubleshooting is totally disregard all the work done before you.
Yeah, yeah. Anybody got any questions out there? Anyone? Bueller. 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 No one's got any questions. Okay, people, it's been fun. You know, I always enjoy it. You know, we're having some interesting times here. I'm still working on that debate with John for the first and second laws of thermodynamics. I am literally working to manifest the rabbit to pull out of my ass. So,
that's what it's going to take. I can't wait.
Chippy's asking Mark, what type of sextant should they buy?
Something that operates as best as possible. I'm not sure what size. Because I know there's different sizes. You got 4-inch, 6-inch, 8-inch, stuff like that. Is that?
Nora's saying any sextant that can take the reading.
Pretty much. You have to have the ability to get the azimuth.
Okay.
Which is the angle from the horizon up to the moon. That's the one that's critically important, and you have to get a relative bearing from where you are in relation to where you're at on the planet. Okay. Or on the Earth, I like to say.
Okay.
So, but just a sextant that's accurate.
Okay.
Because we can do this over a half-hour period, take 10 different readings. So then you can average it all together, so you're not just relying on one set of data.
Yeah. Yeah. So listen, everybody's listening. I think there's like there were 130 something people. There's 121 people watching right now. Listen, people, if you're watching this, please take heed. I put out a video before this hangout regarding the European Southern Observatory's data. All right. If you need to edit it, edit it. You guys know who I am. You know how I speak. I'm not fucking changing the way I do things for any fucking body.
Yeah.
But, I just relax sometimes. I get a little bit too relaxed. Forgive me. I'm not trying to offend anybody. But feel free to edit, mirror, repost any of my videos. With regard to that European Southern Observatory data of where the fixed constellations are, spread that information around, because that is proof of where the stars are. They're within a 20-kilometer zone in the mesosphere, starting at 90 kilometers. That is where the stars are. There's nothing else above it. There can't be. That's why we don't see anything at high altitudes when they launch a balloon or a rocket. It's just pitch black. And what they claim to be the sun, I'm not even sure that's the sun. Because it sure as hell don't look like the sun. But what the hell do I know? I get blinded by it when I look at it here on Earth, so who knows? But we know where the stars are, and if we know where the stars are, that means as big as the moon is, when we see it in the nighttime sky, the moon is definitely closer than where the stars are. Because if the stars, as small as they are or large as they are, at 90 to 110 kilometers, the moon has got to be under 90 kilometers. The moon has to be. Period. Run with that video. Let everyone know. So everyone can start adjusting their models, adjusting their constructs and their designs around where they think everything is, what it may be, because ESO told us there's sodium atoms being excited and heated up so they can glow. So does that mean that all stars are sodium? No. That just means that we still don't know what the hell stars are, but we know where they are. So let's go from there. Mirror the video. I don't have any sort of problems with people mirroring it. But if you're gonna change shit that I say and put your own spin on it, then at least take my fucking voice out of the goddamn video.
Yeah.
You know, telling people I like fucking lemon meringue pie and shit when I'm talking about chocolate cake.
You mean you don't like lemon meringue pie?
I actually do.
Okay.
All right, people. Like I said, it's not what you know, it's what you can prove. I really appreciate it. People have been good, and I guess we either may see you guys this weekend. Maybe we'll do a show if I can get this thermodynamic thing down. If not, we'll see you next week. All right, peeps. Take care of yourselves. Be good to each other. Peace out.
Later.